welcome to lecture 16 of Fox, conditional probability. Or, how do you update a probability when you get new information? Okay, so that's what we will be talking about today. But before we get going, let's talk about what we did last time. Last time we talked about computing probabilities. Okay, so the idea here is you're doing an experiment, okay, and this experiment has an uncertain outcome. So there's a set of possible outcomes. You just don't know which one is going to occur. So, the first thing you do is to set up what's called the probability space. It's a fancy word for just saying, tell me the set of possible outcomes and associate to each possible outcome a probability. Okay? And one of the methods, and one of the most popular methods for getting this probability space, especially when you're working with a real-world experiment, is the outcome tree method, which breaks down the experiment into steps, and each step causes the tree to branch. And then once you collect all this branching together, at the leaves of this tree, you have your outcomes, and then you assign probabilities to each branch in the tree, and then you multiply probabilities, to get the probabilities of each outcome. So we discussed that last time. Okay. And once you have the probability space, you're ready to ask questions. And the answer to the question is usually some subset of this probability, of this set of possible outcomes, which we call the sample space. Okay. And that subset is called an event. And you can compute the probability of the event by just adding up the probabilities inside the event. Okay, so that's how we compute a probability. Now, a very convenient situation is when the probability space is uniform. What that means is the outcomes, however many you have, are all equally likely. Okay, and here are a couple of examples from the real world. If you flip 10 coins, okay, so you get this big tree. Okay. At the leaves of the tree will have 2 to the 10 outcomes, and you could ask, what's the probability of a particular sequence like this? Okay. And that's the outcome of flipping 10 coins one by one. Okay. Now remember, the order of the order in which the coins came up heads and tails could define different outcomes. Okay. But the thing is that each outcome has the same probability, okay, which is 1 over 2 to the 10. Okay, so now we could ask a question like, what are the chances you get 4 heads? And you can sit down and try to quickly compute this, if you can, to sort of test how well you absorb the material from last lecture. Okay, another example, you roll 3 dice. So each sequence for the 3 dice, for example, a 2, you roll a 2, then a 4, then a 5. Each of those has equal probability. So you could ask a question like, what are the chances that you roll at least 2 5s? Okay. So 2 5s or 3 5s. Okay. Now, why is the uniform probability space very convenient? It's very convenient because the probability of an event is basically related to the number of outcomes in the event. Remember, an event is a set of outcomes. Okay. So that means that in uniform probability spaces, computing the probability of an event just basically amounts to counting. And we already studied counting. So the tools of counting are very useful when it comes to doing discrete probability, which is the kind of probability that we are focusing on. Now, we ended last lecture with a sort of an interesting twist. What happens if you're doing an experiment that could possibly go on forever? For example, what happens if you're tossing a coin until you get a heads? Now you might think, well, why would I ever do that? Well, we do it very often in practice. For example, we try to send a packet and we'll keep trying to send it until it reaches the destination. Until it reaches the destination. Or we try to access the Wi-Fi router and we'll keep trying to access the Wi-Fi router until we succeed. Okay, so this concept of trying something until you succeed is very common in real life. Okay? So, this is what we studied last time. Today, we're going to talk about conditional probability. Now, if you thought probability was very, very subtle, conditional probability is an order of magnitude more subtle. It's very subtle. Okay? And, as we will see when we talk about conditional probability traps, okay, if you don't compute the right conditional probability, you can get very messed up conclusions. Okay? But what's the basic idea here? Well, the basic idea here is that, once you've computed a probability, that's all well and good, but now someone might come along and tell you something new, you get some new information, and, just like every good detective will update their conclusions based on the arrival of new evidence, okay, when you get new information, you have to change the probability that you previously computed. Okay? And when you change this probability to a new probability, because you got this new information, we call that a conditional probability. That's all there is to it. Okay? So we will have to develop this this mechanics for how do you update this probability when you get new information, and we'll work out many examples of how you implement this mechanics. Okay, but the basic idea is what do you do about evaluating your chances of something when you get new information. Okay? And new information is always coming in when we talk about real world applications of probability. Okay, finally we'll end with a very important tool. It's similar to the sum rule in counting. Okay, we call it the law of total probability. So you're trying to compute the probability of some event. Okay, and if you can break it down into two specific events, you can then compute the probabilities of those two events. Okay, and add, roughly speaking. Okay, and this is called the law of total probability. So it allows us to do analysis of probabilities using case-by-case approach. just like when we were counting, if you can break down your complex objects into two types and count each type, now you can add. Okay, you can think of that as a case-by-case analysis. We'll develop an analogous tool for probabilities. Okay, so what's this business of updating a probability when new information arrives? Okay, so let's see how the arrival of new information can require us to change a probability. And let's take the concrete example of a flu. So if you randomly pick a person, chances are about 1%. Let's say that they have a flu. So you, for example, have a flu with probability 0.01 or 1%. So the probability of a flu, which we will say probability of a flu, is approximately 0.01. Assuming that you are a random generic person that we could have just picked from a crowd. Okay, but now supposing I come to your house and I find out that you have a slight fever. This is new information. Okay? And before you were just a random person, but now you're a random person who has a slight fever. That additional new information increases the chances of a flu. Okay? And what we say is that your probability of a flu, given the fever, given that we have this new information that you have a fever. Okay, and we write this probability of flu, and we use this vertical bar, given that you have a fever. So the probability of a flu, given that you have a fever, has now gone, much higher, has increased because, now you're no longer just a random person, you're a random person, and we're armed with the additional information you have a fever. Maybe it's about 40% or 0.4. Okay, so this new information changes the probability. Okay, it changes it into what we call a conditional probability. Sometimes people call it a posterior probability. Basically, it's the updated probability of of flu, given the new information that you have a fever. And we can, do this for any two events in general. So we will say that the probability of A given B is the updated probability of the event A, now that you know that the event B has occurred. We call this the conditional probability, and this here is the notation that we use for a conditional probability. It just says that we have had to update the probability of the event A because we got new information. And now let's see, supposing now I also find out an additional piece of new information, that your roommate has a flu. Well, now I have two additional pieces of information. You have a fever, your roommate has a flu. Now the probability of flu given what? Given that you have a fever and that your roommate has a flu, okay? So the probability of flu given a fever and roommate flu is now much, much higher than, 40% because, all the conditions seem to point now to the fact that you have a flu, okay? So in this conditional probability, you see, we're interested in the probability that you have a flu. So in all cases, we're interested in the probability that you have a flu, and all we're doing is updating that. Okay, and on the right of this vertical bar, the given is what's the new knowledge that we're using, what's the new information we're using to update that probability. Okay, now, interesting, very peculiar things can happen when new information arrives. Okay, and, as Sherlock Holmes used to say, once you have eliminated the probable, whatever remains, however improbable, must be so. And that's what, new information can do to a probability. It can take a probability that, for example, is very, very low, it's almost inconceivable, but the new information comes along and makes it the likely outcome. So let me give you an example of that in a pop quiz, which you can think about. Okay? What's the probability that humans are alive tomorrow? Most people would say, that's astronomically close to 1. Okay? Or the probability that there are no humans tomorrow is basically 0. Okay? What's the probability that the sun does not rise tomorrow? So what's the probability of no sun tomorrow? It's probably astronomically, it's probably close to 0. Chances are basically 100% that we will have a sun tomorrow. But now, supposing I told you, there's no sun tomorrow. For whatever reason, there's not going to be a sun tomorrow. Okay, so now you probably infer, oh, something serious has happened. Maybe the thing went supernova or something exploded. So now we can ask, what's the probability that humans are alive tomorrow, given that there is no sun tomorrow? Now think about this. Okay. Probability of humans alive tomorrow, just what we call the unconditional probability, is high, approximately 1. But if I give you this new information that there's no sun tomorrow, you're going to have to change that. Probably something weird happened, and that's the end of humanity. Okay? And now the chances of having humans alive tomorrow, given this new information, is probably close to 0. Okay? So you see how new information it's not that new information can slightly change a probability. New information can completely change a probability. And this is what leads to a lot of mess ups, because conditioning, this arrival of new information, is very subtle. And if you don't take it into account correctly, or you fail to update your probability because of the new information, you're going to make huge, mess ups. Okay, you're going to have a completely distorted view of the experiment, because the experiment can completely change if you get new information. Okay, so while you ponder these real world examples, let's set up a formal infrastructure for computing conditional probability, which is interpreted as the update of a probability when new information arrives, and we're going to do this on the board. Okay, so let's do a concrete quantitative example of how a probability changes when you get new information. Okay, so think of a school, for example, RPI, and let's say that number of students is equal to 5,000. And CS, being the biggest major, has 1,000 of these students. So number for CS is equal to 1,000. Okay, and math is about 1/10 of CS. So the number of math equals 100. Okay, and some students are math CS duals. So, math CS duals, well, that's equal to, CS intersection math. Let's say that's 80. Okay, and we can represent this on a Venn diagram if we wanted to. So the picture would look something like this. Okay, so this is all students. Okay, and a large fraction of these students are CS. So a large fraction are CS. So that's CS. Okay, and 1/10 of that are math. So some amount of these are math, but a large fraction of the math intersects with CS, because 80 of these math students are also CS majors. So very similar to the profile in RPI, for example. So a large fraction of the students who are in math are also intersecting with CS. So math is 100, and this intersection region is 80. Okay, now we're going to imagine an experiment. Pick a student randomly. Pick random student. Okay, so what's the sample space? So sample space omega is, all the possible students can be the outcome. Is all 5,000 students. Okay, and each outcome corresponds to a single student, and each student is equally likely. So, we're in a uniform sample space, and we can ask, what's the probability that you picked a CS student? Okay, so that's the question. How likely is it that you picked a CS student? The event that corresponds to that question is the set of CS students. Remember, an event is a subset of all the possible outcomes. So the probability of CS. Okay, and now in a uniform sample space, this is the size of the event divided by the size of the sample space, because we're in a uniform sample space. So things get much more convenient and easier when we're in uniform sample spaces. You don't need to go through all the details of the outcome tree and so on and so forth. We can immediately look at the outcomes and assign them an equal probability. Okay, and so this is 1,000 divided by 5,000, which is 0.2. So the chances are 20% that if you pick a random student in this scenario, in this experiment, they will be a CS student. No surprise there. Okay, we could have figured that out. 1 in 5. Okay, now you picked a random student, and I'm going to give you some new information. They're a math student. Okay, the student is in math. Okay, so this is new information. And let's see what it does. What does this new information do? Effectively, it shrinks the set of possible outcomes. Okay, before, when I just said you picked a random student and you had no additional information, all 5,000 students were possible. They were possible outcomes, and so that was your sample space. But now that I tell you the student is in math, that eliminates, a lot of those possible outcomes and says that your possible outcomes are now in this set, which is math. Okay? So all of a sudden, your sample space, the set of possible outcomes, your sample space became just the set of math students. That's effectively what this piece of new information does. Okay. Now we can ask, what's the probability of what are the chances that this student who was random, but now we have the new information that they're in math, what are the chances they're a CS major? So we can ask, what are the chances that the student with this additional information is in CS? And the way we indicate that we have this additional indication, we say probability of CS given math. Okay, and so this is, the size of the event in this new sample space that corresponds to CS. But the size of the event in this new sample space that corresponds to CS, the event itself, the set of outcomes that correspond to CS in this new sample space, is exactly the students in this region. Okay, because those are the CS students in this new sample space of possible outcomes. Okay, so the probability of CS given math is the size of this event. But what is this event? That's CS intersection math. Because it's a uniform sample space, okay, because it's still a random student who happens to be math. So it's the size of, the event in this new sample space divided by the size of the sample space, which became math, okay, which is equal to the CS intersection math. The size of that is the number of CS math duals, that's 80, divided by the size of math, 100, which is equal to 0.8. Interesting. Okay, so you see how the arrival of new information changed the probability. So before, when I just picked a random student, the chances are 20% that they're a CS major. Now, if I pick a random student and find out they're in math, the chances are 80% that they're a CS major. Okay. Huge change in the probability. Now, practice. Compute the probability that, a random student is a math major if you are told the additional information that they're in CS. Okay. And compute the probability that a random student is a CS major if you're told the additional information that they're in CS or math. Okay. So, this is practice for you to see if you can apply this reasoning to these two problems. Okay, and we'll move on. Okay, because the uniform sample space where you pick a student randomly is just a special case of an experiment. So let's move on to the more general case of an experiment and see how new information in a more general setting updates a probability. Okay, so this is now the beginning of what we're going to call the definition of conditional probability. So conditional probability. Okay, so the way we write this is you have two events A and B. Okay, so you have a sample space omega space, and you have two events A, that's an event, and B, that's an event. Okay, and we write the probability of the event A occurring, okay, given that B has occurred. Okay, so the probability of event A occurring given that B has occurred, and this is read, the probability, the conditional probability, So conditional being says that, I'm conditioning on the information that the event B has occurred. So conditional probability of A given B. Okay, and this vertical bar is what indicates the given B. Okay, so probability of A given B. Okay, and let's try to work this out. Okay, now, you're doing an experiment, okay, and there's the whole sample space of possible outcomes. So when you're doing this experiment, I'll just heuristically say that, so this is one experiment, this is another. So if you repeated this experiment many times, okay, you get outcome. All these outcomes are in the sample space. And some of these outcomes are in the event B. So what does it mean, are in the event B? Doesn't an event just happen? So now you have to go back and remember that an event is a subset of the outcomes. So when an outcome occurs, okay, we can ask, is it in the subset B? So in some of these outcomes, the event B occurred. Let's call it N sub B. In some of those outcomes, the event B occurred. Okay. So if I tell you now that the event B has occurred, then these other outcomes could not have happened. So this becomes your effective sort of sample space of outcomes that are, possible. For you've eliminated these outcomes. Okay. If I tell you that B occurs. Okay. Now, in some of these outcomes, A occurs. Okay. In some of these outcomes, A occurs. Okay. And then in some of these outcomes, which are box, okay, A and B occur. So A and B. Okay. Now, if I tell you that B has occurred, that eliminates all these outcomes, and associated with those outcomes are the ones that A occurred without B occurring. Okay. So if I ask you now, given that these outcomes did not occur, okay, so it means that when you repeat this experiment many times and make use of the information that the outcomes in B did not occur, you can eliminate these outcomes. Okay, and so the outcomes that become of interest to you are exactly these outcomes. Okay, and so if you repeat this outcome in which you are guaranteed that B occurs, okay, you'll get N sub B outcomes. And by the frequency interpretation of probability, the probability of A, given that B has occurred, okay, is the fraction of those outcomes in this repeated experiment where A occurred, okay, which is N sub A intersection B divided by B, divided by N sub B. So think of it this way: you've run an experiment, okay, and you are now told that B occurred. So you know that the outcome is in B. So it's not one of these. It's this guy, let's say. And then you ran the experiment again, and B occurred, and B occurred, and B occurred. And now you're interested in what's the probability that A occurs, given that B occurs. Okay. So by the frequency interpretation of probability, the probability that A occurs, given that B occurs, is exactly the number of times A and B occurred, divided by the number of times B occurred. So this is, let me write this as, this should approximate that. So whatever this is, it should approximate that. Okay, but now let's rewrite both of these quantities by dividing and multiplying by n. Okay, the total number of times the experiment was done, and then you threw away some of those. So this is equal to N sub A intersection B divided by n. The complication here is the n sub B in the denominator. So N sub A intersection B divided by n times n divided by N sub B. Okay, this is just an equality. Okay. I can write this expression as the number of times A and B occurred divided by n times the number of times B occurred in the denominator with n on the numerator. So this here is the frequency interpretation of the probability. So this is still a probability of A. It's just in this restricted situation where B occurs. So this is the frequency interpretation of probability. Okay. And this is just an equality. You can't argue with that. But now I'm going to use the frequency interpretation of probability again. And we know that, if you run the experiment n times, so this is all the n times you ran the experiment, N sub A intersection B divided by n, this is exactly the probability that A intersection B occurs. Remember, A and B are events, so I can take the intersection to get another set, which is an event. Okay? And this is exactly, 1 over the probability that B occurs. 1 over the probability that B occurs. Why? Because the probability that B occurs is the number of times it occurs, approximately, in the frequency interpretation of probability. It's approximately the number of times that B occurs divided by n. So this, again, is the frequency interpretation of probability. In this case, it's the frequency interpretation of the probability that the event A intersection B occurs, and this is the frequency interpretation of the probability that B occurs. And here, we gave a frequency interpretation of what it means to consider the probability of A given B. You're considering the how often the outcome is in both A and B, as a fraction of this restricted universe, this restricted sample space of only outcomes in B. Okay? And so, what this means is that if we define this conditional probability as this quantity, then it will indeed be the case that when you run this experiment many times and you look at the number of times A and B occurred divided by the number of times B occurred, you will get, this quantity, okay, which by definition is now the conditional probability. Okay? So what we have derived / defined, so definition, the conditional probability P of A given B is equal to the probability of A and B divided by the probability of B. Okay. Definition. Now, you might look at this and say, this only makes sense if the probability of B is not equal to 0. Okay. And that is the case. Okay, so this assumes that when the probability of B is not equal to 0. So this is a definition of the conditional probability. Okay, now we're going to do several examples. Okay, so erase, come back and do some examples. So that's the definition. What's the interpretation? The interpretation is, initially you might have had the probability of A. So you had the probability of A. And now when you tell me the event B has occurred, I update the probability of A to the probability of A given B, which is given by this definition, which corresponds to, observing the experiment many times and looking at how many times both A and B occurred divided by the number of times that B occurred. Okay. Now I want to emphasize, even though it's wrapped up in this fancy language, it is still just a probability. It's just that it's still a probability for outcomes in A. It's just that we have narrowed down the scope to now knowing that B has also occurred. So it's still the probability that A occurs. It's just that it's an updated probability for A. It's an updated probability for A given that B occurs. Okay? Examples. Example 1. It's cloudy 1 in 5 days. So clouds 1 in 5 days. Okay, so what that means is if you picked a random day, the chances of clouds are 1 in 5. Okay. It rains 1 in 7 days. 1 in 7 days. So if you picked a random day, the chances of rain, the probability of rain is 1 over 7. This is approximately correct for the Northeast. Okay. Now, the question, what are the chances of rain on a cloudy day? Chances of rain on a cloudy day. So let's pin down exactly what we're asking for. We're asking for, if you picked a random day and I told you that it's cloudy, then what are the chances of rain? Effectively, we're asking, what's the probability of rain given clouds? And now we can just apply the formula, which says that this is a conditional probability. We need to update the probability of rain from 1/7 to take into account the new information that it's a cloudy day. Okay. So this is the probability of rain and clouds. So intersection means and clouds, divided by the probability of clouds. Now you can just take this as a definition of conditional probability, even though we derived it. Okay. And, what is this? Well, it looks like we can't compute it. We know the probability of clouds. We don't know the probability of the intersection until we think about it a little bit. In the real world, you can't have a rainy day without clouds. So the situation looks like this. Here are all days, and then here are the cloudy days. Okay. And the rainy days are a subset of the cloudy days. Okay. So this means that rain is a subset of clouds. So rain, intersection clouds, So the rainy days intersection the cloudy days is exactly equal to the rainy days, rain. So this is the probability of rain divided by the probability of clouds, which is equal to 1 over 7 divided by 1 over 5, which is equal to 5 over 7. Okay, interesting. So random day, the chances are about 15%, 14, 15% that it's, a rainy day. But, if you tell me that it's a cloudy day, then on roughly 70%, 5 out of 7 cloudy days, it rains. 70% of cloudy days are rainy. So giving me this additional information that it's cloudy significantly changes the chances of rain. And we are all familiar with this phenomenon in the real world. On cloudy days, you're much more likely to get rain than on a random day. Okay, let's do another example. Example 2. Roll a pair of dice. Okay, so now let's think about the outcomes. The first die can be 1, 2, 3, 4 up to 6. The second die can be 1, 2, 3, 4 up to 6. So a useful, convenient way to represent the outcomes, okay, is using a grid. So I'll draw it like this. So this is die 1, I'll call it D1. This is die 2. Okay, it can be 1, 2, 3, 4, 5, 6. Die 2 can be 1, 2, 3, 4, 5, 6. And so what are the possible outcomes? The possible outcomes are all the grid squares, all the grid points. So here are the possible outcomes. Okay, I'm getting good at drawing little dots. Look at this. Okay, now, if you do the outcome tree, so the first die can have one of 6 outcomes, and then for each of those, you can branch out another 6-fold. Okay, so you'll get 36 total outcomes, 6 times 6, and you'll see that the probabilities are 1/6 times 1/6, and it's the same for all the outcomes. So it's a uniform probability space. So it's a uniform probability space. So all outcome probabilities, okay, are 1 over the number of outcomes, 1 over the size of the sample space, because it's a uniform probability space, and you can get this also from the outcome tree. It's 1 over 36. 1 over 36. Okay, let's ask some questions. What are the chances that you roll a sum of 10? Probability that sum equals 10. Okay, so we need to identify the event sum equals 10. The sum equals 10, it can you either get a 6 followed by a 4, a 5 followed by a 5, or a 4 followed by a 6. So let me highlight those outcomes. So it's a set of outcomes. So this is very important. An event is a set, a subset of all the possible outcomes. So the probability that the sum equals 10 is, because we're in a uniform probability space, it's just the number of outcomes divided by the size of the sample space. So this probability is just equal to 3 over 36, which is 1 over 12. Okay, the chances are 1 in 12 that you roll a sum of 10. Let's ask another question. What are the chances that both die are odd? What are the chances that both are odd? Okay, so let's identify the outcomes where both are odd. So both are odd. So here, both are odd. 1, 1, 1, 3, 1, 5. 2, both are not odd. 3, 1, 3, 3, 3, 5. 5, 5, 1, 5, 3, 5, 5. Okay, and if we count up the number of outcomes where both are odd, you see it's clearly 9. So the probability that both are odd is 9 over 36, which is 1 over 4. Okay. Let's compute the conditional probability that the sum is 10 given that both are odd. Okay. So if I'm now interested in the probability that the sum is 10 and I've rolled a pair of dice, okay, and I tell you that both are odd, that's new information. So the probability that the sum equals 10 given that both are odd. Okay, so now this guy is, we just applied a definition of conditional probability. So mechanical approach to computing conditional probability. The probability that the sum is 10 given that both are odd is just equal to the probability that the sum is 10 and both are odd divided by the probability that both are odd. So this is the mechanical approach. We derived it. It has a frequency interpretation of, when you run this experiment and only focus on the situations where both are odd, because that's, what information you're given, then the frequency, the fraction of those outcomes where both are odd will be this conditional probability. Okay. And now we need the intersection of the sum being odd and both being, the sum being 10 and both being odd. Well, so we need to look at the intersection of these two sets, and there's only one outcome here. And so the probability that the sum is 10 given that both are odd is just 1 over 36 divided by the probability that both are odd. Both are odd is 1/4, 1 over 4. So this is 4 over 36, which is 1 over 9. There. So the chances that you have rolled a 10, if you know that both your rolls are odd, is 1/9, okay, which is slightly higher than the chances of rolling a 10. Okay, it's slightly higher than the chances of rolling a 10. Okay, so exercises. Compute exercise. Compute the probability that both are odd given that the sum equals 10. So this is what we call the transposed conditional. So I flipped the probability you're interested in and the information you have. So now I'm asking you, you roll a pair of dice and I'm telling you that the sum is odd. What are the chances that both are odd? I'm telling you that the sum is 10. What are the chances that both are odd? Okay. So pause the video for a couple of seconds. 1, 2, 3, 4, 5. And if you're coming back and if you compute it, I'm going to tell you the answer. Okay, so the answer here is, we need to compute the intersection, but that's the same. So it's 1 over 36 divided by, now we need the probability that the sum is 10. The probability that the sum is 10 is 1/12. Okay, so this is equal to 12 over 36, which is 1 over 4. Okay. 1 over 3. Okay, 1 over 3. 12 over 36, which is 1 over 3. So look, okay, the probability that both are odd is 1 over 4. Now, if you tell me additionally that I'm giving you the additional information that the sum is 10, now the chances that both are odd has gone up to 1/3. So probabilities get updated when you get new information. And interesting, okay, the probability of A given B is not the same as the probability of B given A. In general, okay, do not assume that the probability of A given B is not generally equal to the probability of B given A. Okay. So now let's summarize the mechanics for computing a conditional probability. Okay, so let's erase. And compute and summarize conditional probability mechanics. Mechanics for conditional probability. Okay. And it's not very different. It's not much more complicated than computing a probability. So, so some people might say, oh, computing conditional probability is very hard, and so on and so forth. It's not. And it's all due to this fundamental formula that relates this conditional probability to the ratio of two regular probabilities. Okay. So the conditional probability is the ratio of two regular probabilities. Because A intersection B is a set, it's an event, and B is an event, it's a set. So if you can compute regular probabilities, you can compute conditional probabilities. Okay? Now, so here's sort of a cheat sheet. Here's a workflow. So the first thing you need to understand is that you're being asked to compute a probability and you're being given some side information. So you need to sort of realize that conditional probability is relevant. You need a probability and you are given some side information. For example, what are the chances of rain given cloudy? Okay. What are the chances of a sum being 10 given that both are odd? Okay. So you're asked for a probability and you're given some additional side information. Okay. So the first thing you do, so probability is relevant. Okay. So you need to compute, just as we did, for example, with the dice, you need to compute your sample space, the possible outcomes, and the probabilities associated with them. So figure out the probability space. So this is the samples, the possible outcomes, the sample space, and the associated probabilities. Okay? And you can use the outcome tree method, for example, to get this. So if it's a uniform probability space, things might be easier. Okay? So for example, outcome tree method. Okay? Now, you need to take the question you're asked and identify from within this sample space, what are the sets A and B. So identify the events A and B. Okay. So for example, in our case, we said what are the chances of rolling a 10 given that both are odd. So rolling a 10 corresponded to an event, a subset of 3 outcomes, and both being odd corresponded to a subset, an event of 9 outcomes. So you have to identify the events A and B. Okay. Then you have to compute regular probabilities. Okay. So in the normal way, you compute regular probabilities P of A, P of B, and P of A intersection B. So how do you compute regular probabilities? For each outcome in the corresponding event, you just add up the outcome probabilities. And you know all the outcome probabilities, and you know the events A and B, so you also know the event A intersection B. And then you just apply the formula. Very simple. Okay, the probability of A given B, you set this equal to the probability of A and B divided by the probability of B. Okay, so technically you don't need the probability of A for this guy, but if you wanted the other guy, probability of B given A is equal to the probability of A and B divided by the probability of A. Okay. And it's very important to realize that these two are not generally equal to each other. Okay, so that's the workflow for computing conditional probabilities. It's not really much harder than computing regular probabilities because we have related conditional probability to regular probabilities. That is the entire point of this formula, this definition. Okay, let's erase and do more examples. Now we will do speed erase. Bam, bam. Let me tell you about a couple more examples of conditioning of the arrival of new information, and then we'll talk about conditional probability traps. Okay, let's go back to the Monty Hall game. So the Monty Hall game. Okay. And remember, so the contestant is at door 1, the prize is at one of the 3 doors, door 1, 2, or 3, and Monty opens either door 2 or door 3 in the case that the prize is behind door. So if the prize is behind door 1, so this is the outcome 1, 2. This is the outcome 1, 3. Okay, and here he has to open door 3, so this is the outcome 2, 3. And here he has to open door 2, so this is the outcome 3, 2. Okay, but now I'm going to add a twist. So, the prize is randomly placed behind a door, so this is 1/3, 1/3, 1/3. Okay, but now I'm going to add a twist, which is that Monty, if he has both doors available to open, prefers to open door 3. Okay, so in this case, he has only one door to open, which is door 2. Okay, in this case, he has only one door to open, which is door 3. Okay, but here he prefers door 3 to 2. So 2/3 of the time he will open door 3, and 1/3 of the time he will open door 2. Okay, so that's just, Monty has just a preference. If he can, he'll open door 3. Okay, now, exercises for you. Prove, show, compute the probability to win by switching. Okay, and this is, we already computed it, and the intuitive argument is he wins whenever the prize is behind either door 2 or 3, if you switch. Okay, so let's compute the probabilities. 1 times 1/3 is 1/3. 1 times 1/3 is 1/3. Now we have 2/3 times 1/3, which is 2/9, and 1/3 times 1/3, which is 1/9. Before they were 1/6, 1/6. Okay. Now you still win in these two outcomes by switching, and so the chances of winning by switching is 2/3. Okay. Now I'm going to give you some additional information. You're playing the game, and Monty opens door 2. Okay. Monty opens door 2. And I claim you should be jumping up and down for joy. Why? Okay, so let's think about this. Well, Monty prefers door 3. Okay? Because if both doors were available, he prefers door 3. So why did he open door 2? He opened door 2 probably because he couldn't open door 3. He prefers door 3. Again, why wouldn't he be able to open door 3? Okay, he wouldn't be able to open door 3 if the prize was behind door 3. So he opened door 2, okay, likely because he would have rather opened door 3, but the prize was there. So you should be jumping up and down for joy. Okay, and now here's the exercise. Compute the probability to win by switching given that Monty opens door 2 and show that this probability is 3/4. So, when you didn't have this additional information, your chances of winning are 2/3, when you didn't know which door Monty opened. So in other words, at the beginning of the game. But now that you have this additional information that Monty is going to open door 2, your chances of winning have gone up. And that corresponds to it confirms the intuition that I gave you that, why wouldn't he open door 3? It must be that the prize is there. Okay. So here's another, and this is a more subtle example. Okay, so I'm gonna show it to you, and then I'm gonna ask you to read the text, and which analyzes this example very carefully. Okay, and if you can analyze this example on your own, then you've basically understood probabilities and how to update probabilities when new information comes. So let me call it a case of 2 boys. Okay, so you have 4 friends, A, B, C, and D, and here's what you know about them. Okay, they each have 2 children. They each have 2 children. Okay. Now, let's ask the question, what are the chances that their 2 children are boys? What's the probability of 2 boys? Okay, and now here we have to make some assumptions. And we're going to make the assumption that, having kids is like flipping coins. Each time you have a kid, it's like flipping a coin, a fair coin, and half the time it's going to be a girl and half the time it's going to be a boy. Okay, so asking what are the chances that, anyone has 2 boys is exactly the same as asking you flip 2 coins, what are the chances you get 2 heads? Okay, so that's 1/4 times 1/4. So this is 1/4. Okay, now I'm going to give you additional information, new information. Okay, new information, 1. So in this case, you know that A has at least 1 boy. A has at least 1 boy. So what is the probability now that you have this additional information, the probability of 2 boys, given at least 1 boy? Okay, so that's the exercise. Okay, and I'm going to tell you the answers. Okay, now you might think, well, what's changed? What's changed is that you have this new information that A has at least 1 boy. Okay? And now you're asking, what are the chances of 2 boys? Here you didn't know anything else and you were asking, what are the chances of 2 boys? Okay. Now, so let's see if I can give you the intuition here. So if you know that he has at least 2 boys, then what are the cases? The cases are that A has a girl followed by a boy followed by a boy followed by a girl, or a boy followed by a boy. Those are the three cases to which you are narrowed down to, when you know that A has at least 1 boy. You know for sure that it cannot be girl. Okay? So of these 3 cases, one of those is 2 boys. So intuition suggests that the probability of 2 boys, given that you know that you have at least 1 boy, you have 2 cases, boy, out of 3 possibilities, boy, girl, boy, so you might suspect it's 1/3, and indeed it's the case. But, you need to be able to get that using conditional probabilities and the method that we have, given you. Okay. So that's, if A has at least 1 boy. B, let me give you some new information about B. B's older child is a boy. Okay. So now, what's the probability of 2 boys? Given that older is a boy. Well, how is this different from that? So that's subtlety of information. This is a subtly different statement, subtly different piece of new information to
to A has at least one boy. This guy, B's older child is a boy. So let's look at the scenarios for B. So if the older child is a boy, then there are only two, we've narrowed down to two scenarios. Either the younger child is a boy, and then you got a boy, or the younger child is a girl, and then you got a boy. So it's girl, boy, or boy, boy. So you have two options, and one of them is boy, boy, so one might suspect, intuition says that this is a half. Okay, and indeed, compute the conditional probability using the method that we prescribe and get a half. That'll show that you know how to compute conditional probabilities. This is worked out carefully in the text, okay, in the chapter. 3, new piece of information. Okay. You were on a walk and you met C. Walking with a child, walking with a boy. Okay. So what is the probability of two boys given that you met a boy? And you might wonder, what? How is this any different from the first situation where you told me that A has at least one boy? Isn't this exactly the same? You met C while walking with a boy. Doesn't that just tell you that C has exactly one boy? This is where conditioning is subtle. Okay. You can imagine that when C goes for a walk, if C has two boys and is picking one of the children to go for a walk, you could have met the first boy or the second boy, and that those are two equally likely scenarios. So what this does is it narrows us down to actually not 3 scenarios as it did here, but it narrows us down to 4 scenarios. Let me tell you what the 4 scenarios are. This is the intuition. Okay. So the first scenario is C has a girl first and then a boy, and you met that older boy. Okay. Or you met that younger boy. Then C has a boy first and then a girl, and you met that older boy. Okay. Or C has 2 boys, boy 1 and boy 2, and you met boy 1. C has 2 boys, boy 1 and boy 2, and you met boy 2. So there are 4 scenarios now that are consistent with you met a boy while walking and encountering C on a walk. Okay. And of those 4 scenarios, 2 consist of 2 boys. So we might suspect that this is 2 over 4. But now it's very subtle and complex. So I'm suggesting that may be 2 over 4, which is a half. But the reasoning I gave for it is very subtle and complex. And how do I know to think of 4 scenarios? What if I thought of 3 scenarios, and so on and so forth? Okay. So this is why you have to use the prescription, the mechanism, the mechanical approach to computing the conditional probability. Okay. And you should be able to get 1/2. And if you cannot, it's done carefully in the book. Okay. Now, 4th case. Okay. D is Klingon. So that was the famous sci-fi, TV series in my time. Okay, Star Trek. Okay, so D is Klingon, and Klingons always take boys for a walk. Klingon, so always take boys for walk, if it's possible. So if they're going for a walk and they're taking a kid, if they have the choice to take a boy, they take a boy. That's Klingon, maniacs. Okay. So now you met D on a walk with a boy. Met D on a walk with a boy. Okay. They always take boys for a walk. Okay. So, what are the chances that, D has 2 boys? Probability of 2 boys given that you met a boy. Okay. And now, ironically, the chances of 2 boys given that, you met a boy on a walk is exactly equal to 1/3. So this scenario where D always takes boys for a walk is exactly the same as the scenario where I tell you that D has at least 1 boy. Because if you meet a boy on a walk with D, all you can conclude is that D has at least 1 boy. Because you know that whenever D has a boy, D will take the boy on a walk. So this and this scenario are the same. It's subtle. So you need to resort to the mechanical approach to computing conditional probabilities. It's covered carefully in the book. Okay? And you should be able to derive that 1/3 without having to do this subtle reasoning. This is the problem with new information. It can be subtle. Okay? So read the text carefully for this example, okay, and do them on your own, okay, and practice. Because conditioning is very subtle. Let me erase, and we'll come back and talk about conditional probability traps. Okay, so let's talk about conditional probability traps or errors that people can make, and they're very subtle errors and sometimes leading to very big mistakes, when you use one probability instead of another. Okay, so conditional probability traps. Okay, and the issues arise because we have so many different kinds of probabilities and the differences between them are very subtle. So imagine you have an event A, so you can compute the probability of A. Okay. Now if you have another piece of new information B, you can compute the probability of A given B. So updated probability of A. But there's what's also, this is the conditional probability. There's also what's called the transposed conditional. So the probability of B given A. And we know that these two are not the same. So one mistake that can happen is that you compute one instead of the other. Okay? And then there's also another kind of probability, which is the AND. So if you have two events A and B, there's the probability of A and B. Okay. So now let me tell you about a couple of, conditional probability traps. The first is what's called sampling bias. Okay, sampling bias. Okay. And mathematically, you're basically using probability of A, so the unconditional probability instead of probability of B. Of A given B. And this often occurs in sampling. So you're doing a medical trial, so you sample some people and try a drug. Okay, and one place where this happens a lot is when we try to figure out, we try to sort of estimate, who's going to win an election. Okay, so you can think that all the 250 million voters or 200 million voters or so, that's the sample space. And if you randomly picked a voter, what are the chances that they would vote Republican? So the probability to vote Republican, let's say, is approximately a half, because there's roughly an equal number of Republicans and Democrats, and on any given election, it can go up or down, let's say 0.5% or 1%, okay? So it's approximately a half. But now you want to test this hypothesis. So what you're going to do is you're going to do this experiment. You're going to randomly pick, a voter, ask them, who are you going to vote, and keep doing this. Do this experiment many times. So randomly pick voters and ask. Okay, and you should find that approximately half of the people you picked will say they voted Republican. Okay, but now when you do this experiment, how do you actually implement it? So one thing that we could do is we could ask Apple. So we ask Apple, to send a text message to all iPhone users. Okay, so ask all, because they have control of the iPhones. Let's say iPhone users to say how they vote. Okay, so Apple does this and then comes back to you and you find that the fraction that are voting Republican is very much greater than a half. Okay, and you wonder, wow. So does this mean that the frequency interpretation of the probability is dead? No. And that's because, there's a very subtle new information here, which is, who did you ask? You asked people who had an iPhone. Okay. So we didn't compute the probability that a random voter votes Republican. We have computed in this experiment the probability, or we've approximated the probability, that you vote Republican given that you have an iPhone. Okay. That's a very subtle piece of conditioning. It's a subtle piece of new information. And it turns out that this number is much, much greater than a half. And so you'll make this mistake that you'll think that there are way more Republican voters than there actually are, because the way you sampled voters has biased you towards owners of iPhones. Okay, so that's why it's called sampling bias. Okay. And why is this the case? That typically you'll find that Republican voters are a larger fraction than 50% of iPhone owners, because iPhone owners have to be rich. And it tends to be the case in the US that Republicans or people who vote Republican tend to be more pro-business and, wealthier. Okay. For a famous example of this, do a Google search. Okay. On, Dewey defeats Truman. Do a Google search of this. You might be saying, well, what? Dewey? Who is Dewey? Yes, that's exactly the point. Do a Google search on this and you'll see a famous example of this. Okay, I'm going to move on to another example, what's called the fallacy of the transposed conditional. So, the transposed conditional. So the transposed conditional is where you're using probability of A given B when perhaps you should be using the probability of B given A. So using one conditional instead of another of the transposed. Okay, so probability of A given B instead of the probability of B given A. Okay, a famous example of this happened in a study by Lombard, where Lombard wanted to figure out what's the riskiest profession. Okay, so because he had no other way to sort of investigate the riskiness of professions, he went to the morgue, okay, and he surveyed death records. And upon death, he looked at what was your profession. So profession upon death. Okay. And then he also looked at what was your age, so that would tell him about your lifespan. Profession upon death, and also age. And you want to know what the riskiest profession is? Student. Riskiest profession is student. Oh, don't worry. Don't quit. Okay, don't quit yet. Okay. There's a flaw in Lombard's paper, which is he's looking at the transposed conditional instead of the correct conditional. So let's see what he actually did. What he actually did was, okay, so he took all the people who died, let's say, younger than 20. Okay. And then he looks at what's your profession. Oh, they're all students. Then all the people who died between 20 to 30, what's your typical profession? Oh, those guys tend to be in the military or what have you. Okay. So what Lombard was actually tabulating was, what's the probability of, a particular profession, okay, given that you died at a certain age. Because what we see in the data is the age at which you died, and then we can look and see what's your profession. So given that you died, let's say, died at less than or equal to 20. Okay. And no surprise, if you died at less than or equal to 20, then, if you give me that as a piece of information, then it's pretty clear that most of those people who died less than or equal to 20 are students, because you haven't had time to do anything else. What Lombard actually wanted, he wanted the probability that you die at age less than or equal to 20, given your profession. So given that you are a student, what are the chances you die at less equal to 20? Okay, so let's change it now, not to 20, but to, let's say, 30 or 40 or 50. Okay, what are the chances you die at less equal to 30? Given you're a student, given you're in the military, given you're a doctor, and so on and so forth. Okay, so this is the correct conditional that he wants, but he measured this one. Okay, and some strange things occurred here. For example, I think the least risky profession was something like, chocolatier or something like that, or morgue operator. Some weird professions. And that's because those professions only come into play. You only become that if you live long enough. So given that you lived long enough, what's your likely profession? And given that you live long enough, it's almost, impossible that your profession will be listed on your death certificate as student, because you would have done something. Okay? So no students lived long. And all people who died young were students. Wrong conditional, transposed conditional. So let's erase. I'll come back and show you another fallacy of the transposed conditional, and we're going to discuss medical testing. Okay, medical testing. So this is an example where, people tend to fall into this trap of the transposed conditional. So they need one conditional, but they use another, and actually it can lead to some panic. Okay, so we have a lame test. You have a test for lame. Okay, so we've created a test for lame, loud and mostly erroneous behavior. Okay, and let me tell you some of the properties of this test. So, if you are lame, it's a pretty accurate test. 10% error rate. Okay, so this is sometimes called, if you're lame, 10% error rate. This is sometimes called the false negative rate. And if you are not lame, It's a 5% error rate. Okay, so if you're not lame, it says that you're lame 5% of the time. So that's called a false positive rate. Okay, and about 1% of the population is lame. So 1% of population is lame. So you got tested. You were tested and you came up positive. Okay, and now you panic because look at the reasoning. Okay, so could you be not lame? So if you're not lame, okay, that means the test is wrong. Okay, and the probability that test is wrong is very small. Okay, because if you're not lame, it has only a 5% error rate, so the chances are very small that the test is wrong. Okay, so it looks like therefore that you must be lame, because if you're not lame, it's a very unlikely situation. This is kind of like a probabilistic proof by contradiction. Let's see what happens if you're not lame and we come up with something unlikely and therefore you must be lame. Well, there's no such thing as probabilistic proof by contradiction. There's proof by contradiction, but there's no such thing as probabilistic proof by contradiction. And what's the problem what's going wrong here? Actually, what you're looking at here is the probability that the test is wrong, assuming that you're not lame. And that's where you get that this number is very small, because if you're not lame, the test is very accurate. But, this probability is of no use to you because you don't have the information that you're not lame. So you cannot compute a probability conditioned on being not lame. The information you have is that you tested positive. So the probability that you need to look at is the probability that you are not lame, given that the test is positive. Okay, because this is the information you're given, and this is what you would like to know. You'd like to compute the probability of being not lame. Now, if you didn't have the test, the probability of being not lame is 99%, because 1% of the population is lame. But now that you have the test, let's see what's the probability that you are not lame. We can just, blindly use a mechanical approach to computing conditional probability. So let's do the experiment. The experiment starts with you. Okay, so you can either be lame or you can be not lame. Okay, and now you're going to get the test. In either case, the test can either say yes or no. Yes or no. Okay, and in this case, you're lame, and the test said yes. In this case, you're lame, and the test said no. In this case, you're not lame, and the test said yes. And in this case, you're not lame, and the test said no. So there are 4 outcomes of this experiment where we decide whether or not you are lame and then what the test says. Okay, now the chances you are lame is just 1 over 100, 1%. The chances you're not lame, 99 over 100. Okay, and the chances that, now if you are lame, in this situation, the test gets it wrong, with the chance the test gets it wrong is 10%. So it's going to say no, chances are 10 over 100. Okay, 10%. And the chances that it says yes are 90 over 100. Okay, it's right 90% of the time. And here, the chance that the test gets it wrong, so says yes when you're not lame, is only 5 over 100. And the chance that it says no is 95 over 100. So we can compute the probabilities. Okay, so the probabilities are, multiply 90 times 1 over 10,000 over 100 times 100. So 90 times 1 over, so that's 90 over 10,000. Here we have 10 over 10,000. Here we have 5 times 99 over 10,000. And here we have 95 times 99 over 10,000. Okay, so if you do this experiment with overwhelmingly high probability, the chances are overwhelmingly high that the outcome is not lame and no. But that's not what happened. Okay, what happened is that the test said yes. So one of these things is what happened. Okay, but let's just continue. Let's compute mechanically the probability that we want. So the probability of not lame given yes, okay, is equal to the probability of not lame and yes divided by the probability of yes. That's just the formula for the conditional probability. Now we need to compute those individual regular probabilities. The probability of not lame and yes. So not lame and yes is just one outcome. 5 times 99 over 10,000. So this is 5 times 99 over 10,000. divided by the probability that the test says yes. So what's the event where the test says yes? This outcome and that outcome. So the sum of those outcome probabilities gives us the event probabilities. So the probability of yes is the sum of these two. So 90 over 10,000 plus 5 times 99 over 10,000. Okay, so these cancel out. So this is 5 times 99 over 90 plus 5 times 99. And if you compute this, it's approximately equal to 85%. Wow! Okay, so let's now interpret. There's a rare disease, Lyme. Okay, you took the test for it. So it's rare because only 1% of the population have it. You took the test for it, and it's a pretty accurate test. Okay, and you came up positive. And still, the chances that you are not lame, even though you came up positive, are 85%. It's way more likely than not that you are not lame. Let's see what's going on here. Okay, what's going on here is when the test says yes, okay, one of two things happen. Either you are lame, which is rare, and the test got it right, which is what the test normally does. That's often. Or you are not lame, which is often, and the test got it wrong. So the test is correct, that's often. And the test is wrong, that's rare. Okay? So let's see what's going on. Here, you have the choice of a rare thing followed by a normal thing. And here you have a choice of a normal thing, often thing, followed by a rare thing. Okay? And so there's sort of a balancing between rare and often whenever the test says yes. And in this case, option 2 wins. That it's more likely that the often not lame thing wins, combined with the test being wrong. Okay. And what's going on here? What's going on here is that the background population, the fact that 99% of the people are basically not lame, is overwhelming the test. Okay. And that results in, it's way more likely than not, even though the test says you're positive, it's way more likely than not that you are negative. And this is the situation that's going to happen with any very rare condition. Okay. So most tests for these rare conditions, they're not 100%, so they're pretty accurate, something like this. Okay, maybe slightly more accurate. But, once you have a very rare condition, even when the test says positive, chances are you don't have it. So then what's the use of the test? Okay, well, here's something that you need to know now. For rare conditions, when the test says yes, what should you do? Okay, what you should do is you should ask to be retested. Okay? Because this experiment, so now the experiment continues. Okay, so if it says yes, you try again. And if it says yes again, now you see you're compounding the chances that the test is correct versus the test saying yes, and you're not lame is getting rarer and rarer, and now you're getting a more and more accurate test. Effectively, you are trying to boost the accuracy of the test by repeating. So if it's a rare condition and you test positive, you better get retested before you panic, okay? Because this is what's going on. This is what the conditional probability says. Okay, so now let's erase and move back, and we'll talk about the law of total probability. Okay, so the law of total probability. Law of total probability. Okay, and it's a very simple law. Its derivation is not going to be very hard, but it's so powerful. You really want to know this law. Okay? And in fact, it's sort of the basis of methods for computing probabilities, like a build-up method for probability, just like we had a build-up method for counting. Okay. Now let me just remind you what's the definition of a conditional probability. So P of A given B is equal to P of the probability of A and B, okay, divided by the probability of B. Okay. Now it's very useful sometimes to write this in another way. So this is, if and only, is equivalent to saying that the probability of A and B is equal to the probability of A given B, okay, times the probability of B. So all I did was rearrange this and multiply both sides by the probability of B. Okay, and okay, so here's just a review, a repetition of the definition of a conditional probability. Okay, now let's go back to the sample space. So we have the sample space, which is omega. Okay, so the set of all possible outcomes, and consider an event A. Okay, and we're interested in the probability of the event A. Okay, now suppose that there's another event B, and we've been talking about conditional probabilities and so on and so forth. So let's consider another event. So let's call this event A. Okay, and let's consider another event B. Okay, so this is another event B. Okay, so if this is the event B, then outside of this event B is the event B bar, the complement of B. Okay, and observe that the event B breaks up A into two regions. Okay, so I'm going to call the first region, I'm going to color the first region blue, and I'm going to color the second region red. Okay, and let's see if we can figure out what these two regions are. Well, this region here is easy. This is exactly A intersection B. Okay, no problem. That's the blue region. What about this region? Well, it's A intersected with what's outside B. So this is A intersection with what's outside B. Okay. Now, so the outcomes in A, so A is equal to A intersection B bar, A intersection B, union A intersection B bar. And you can see that these are two disjoint sets. So that the outcomes in A are those in A intersection B together with those in A intersection B bar. So we can compute the probability of A. It's a sum rule for disjoint unions that applies to probability, just like we had the sum rule for counting, for sizes of sets. Okay. So the probability of A sums the probabilities of all outcomes in A. So we can sum the probabilities of all the outcomes in A intersection B. Okay, and add that to the outcomes in A intersection B bar. Okay, so that's the sum rule. So we're just using the sum rule for adding probabilities. We add all the probabilities, or we can add it in two steps. Okay, and now I'm going to use this reformulation of conditional probability. So this guy here is the probability of A given B times the probability of B. So the probability of A intersection B is the probability of A given B times the probability of B, plus the probability of, so it's just A intersection B bar. I replace B by B bar. Probability of A given B bar, complement of B, times the probability of B bar. Okay. So I'm going to box both of these because both of these are very important formulas. Okay. And basically, they allow us to compute the probability of A as a sum of two terms, either the probability of A and B plus the probability of A and B bar, or the probability of A given B weighted by probability of B, plus the probability of A given B bar weighted by the probability of B bar. You can think of this as a case-by-case analysis for probability. Okay, so it's kind of like a probabilistic case-by-case analysis. Okay. And what matters, so we consider the outcomes in A as two cases, those that are in B and those that are in B bar. You can consider more than two cases if you have, for example, a third case. You might have a third case. You can do this for more than two cases, and we might even see some examples of that. But for the moment, this is the fundamental law of total probability. Very powerful. Okay, so let me show you, some of the uses of this law of total probability. So, example. Now, I'm going to show you some examples where it just makes computing probabilities easier, but you can always resort to the outcome tree method. So you have a box. You have a box with 3 coins. Okay, 2 are fair. That means they have a head and a tail, and 1 has both sides heads. Okay, so it's 2-headed. Okay, so it's extremely unfair. You flip it, you can only get heads. So you pick a coin at random. Okay, so you pick a coin at random. So let's start doing this experiment. You pick a coin at random. Okay, and you can either pick, so there are 3 coins. So you can pick the fair coin, fair 1, let's say. You can pick the second fair coin, fair 2, and you can pick the 2-headed coin. Okay, and you pick a coin at random. So each of these choices is equally likely. Okay. Then now you're going to flip the coin, and we're asking what are the chances that you get a heads. So you can flip the coin. If you flip the fair coin, you can either get heads or tails, half, half. Okay, if you flip the fair coin, you get heads or tails, half, half. But if you flip the two-headed coin, you can only get heads. Okay, because it's two-headed. So the chances are probability 1 that you get heads. So what are the outcomes? In this case, the outcome is heads. In this case, tails, heads, tails, heads. And what are the probabilities? 1/6. Okay, 1/6, 1/6, 1/6, and 1/3. Okay. And so you picked a coin and flipped it. Okay. And we can ask what are the chances that you flipped a head? So what's the probability of heads for this experiment? Okay. Well, we need to identify the outcomes. 1, 2, 3 outcomes. And so the probability of heads is here are the 3 outcomes. Okay, so the probability of heads is 1/6 plus 1/6 plus 1/3, which is equal to 2/3. No surprise, because you have a two-headed coin in there, there's some chance that you pick the two-headed coin, so the chances of flipping a head are 2/3. Now let me show you how we can easily compute this number without all this sophistication of the outcome tree. The outcome tree always works, okay, but we're going to try to compute it now using the law of total probability, just to illustrate the law of total probability. Okay. So using the law of total probability, we are interested in the probability of probability of heads. Okay. And we can consider 2 cases. So you can think of this as case-by-case analysis where you have 2 cases. Either B happens or B does not happen. So it's the probability of heads given what? Given that you picked a fair coin. Okay. But now you have to weight it by the probability of fair, plus the probability of heads, given that fair did not happen. So complement of fair. So if fair did not happen, it means you pick two-headed times the probability of two-headed. Okay. And now let's see if we can compute these things. Well, the probability that you pick a fair coin, since there are 2 coins out of 3 that are fair, this is 2/3. The probability of getting a head, if you have picked the fair coin, given the additional information that the coin is fair, well, this we know, this is 1/2. Okay. The probability of the two-headed coin is 1/3, because it's 1 out of 3. One of the coins is two-headed. And the probability of getting a heads, if you have the two-headed coin, is just 1. So this is 1/2 times 2/3 plus 1 times 1/3, which is equal to 1/3 plus 1/3, which is equal to 2/3. Bam! Bam! Okay. So easy. No need of outcome tree, nothing. We're using the law of total probability. Okay. So, let me erase this example and come in and show you something very interesting. Something very interesting. Now, by the way, there's lots of exercises in the book, lots more examples in the text. Okay, so work through the examples in the text and work through all the exercises and pop quizzes, because conditional probability is subtle, and being able to use the law of total probability efficiently and with ease is a very powerful asset. Okay, especially moving forward when you want to compute probabilities. Okay, so I'm going to come and show you something interesting. Okay. All right. Okay, so let me show you something interesting. First, an exercise. So exercise. So practice the law of total probability. So in a box, you have 10 coins. 6 fair and 4 biased. Okay, so biased means that the probability is equal to 2/3 of heads. Okay, so now consider the following 2 experiments, and we're interested in the probability, the chances that you flip 2 heads. So probability to flip 2 heads. And here are the 2 experiments. The first experiment is you pick a coin randomly. A coin randomly and flip 3 times. And now we want to know what are the chances you got 2 heads. Use the total probability to solve, use the law of total probability to solve it. And the second question is, you pick a coin, you flip 3 times. Okay, so you flip 3 times, just like before. Flip 3 times. But each time, for each time pick a random coin Okay. Flip it, and then put it back into the box. Okay? So it's important to understand the difference between these two. In the first case, I just picked a coin once. I randomly picked a coin out of these 10, flipped it 3 times. In the second case, I pick a coin, flip it, put it back. Now randomly pick again, flip, put it back. Randomly pick again, flip, put it back. So analyze these 2 experiments. Okay? Meanwhile, I'm going to show you something very interesting. Well, when I say that, I mean interesting for me, right? I hope it's interesting for you. Okay, so your friend comes to you and says, let's play a game. Okay, heads I win, tails I lose. And I've got a coin. And now you suspect this guy, he's taken Fox. Maybe he's got a biased coin. Okay, so, friend has biased coin. Question mark. Maybe, you don't know. You'd like to trust the guy, okay, but, you don't know, okay. Is it going to be a fair coin? So what you're going to do is instead of putting the guy on the spot, putting your friend on the spot, you propose, okay, let's play heads I win, tails I lose, tails you win, okay? And we'll use your coin, which I'm going to, which I'm going to sort of trust is fair, but I'm going to somehow manage to ensure that it is fair. Okay. So is it possible to create a fair coin from a biased coin? Question. Is it possible to create a fair coin from a biased coin? Okay. Without knowing that the probability that the coin flips heads. Okay. Without knowing the probability coin flips heads. Okay. So let's call the probability that the coin flips heads, let's call it P. So idea for a fair coin, P is a half. So P equals probability to flip heads. Okay. So here's my suggestion. Okay. You don't flip the coin once, you flip the coin 2 times. Okay. Now in the first flip, the coin can either turn up heads or tails. Okay. The problem is you don't know what the chances of heads are, and so you don't want to be done here because what if, P is very high and then, your friend is winning all the time. So this could be P and you don't know what P is. We will assume that it's not 0 or 1. Okay. So it's not a deterministic coin. It has randomness. Okay. So P. And this is going to be 1 minus P. Why 1 minus P? Because these 2 must add up to 1. Okay. Now flip it again. Okay, so if you flip it again, this is P with going to be heads, 1 minus P, it's going to be tails. Okay, and if you flip it again, in this case it's going to be heads with probability P, and tails with probability 1 minus P. Okay, good. Okay, so these are the outcome, and let's see. So the outcome is, heads with probability P squared, heads tails with probability P 1 minus P, tails heads with probability P times 1 minus P times 1 minus P, 1 minus P in that case. And here you get tails with probability 1 minus P, 1 minus P. So 1 minus P squared. Okay. So now here's the idea. Look, heads, tails, and tails, heads has the same probability. Okay. So what we're going to do is we're going to say if you flip twice and it's heads, tails, we'll count that as a heads. So we'll count this as, I'll call it a heads. I'll put it in blue heads. Okay. And if it flips tails heads, then we'll count that as a tails. And now what we know for sure is that the chances of heads and tails are exactly the same independent of P. Okay. Now, what do you do in the other cases? In the other cases, what we'll say is we restart. It's a foul flip. Okay, foul. Restart. Okay, so foul. Restart. Now, you see that it's possible that this coin flipping to just get 1 heads or 1 tails could go on forever if you just always flip heads. Okay, so this is an example, just like in the last lecture where we were flipping a coin till you got a head. This is an example of an experiment that may never end. Okay, you can arbitrarily keep going tail, tail, then head, head, then tail, tail, and keep restarting. Okay, but when you stop, it'll either output heads or tails. And it sounds like the tails and heads will be output with equal probability. So now we've constructed a fair coin from a biased coin. That's like a miracle. I don't even need to know the bias. Okay, so let's prove it. And we're going to prove it using the law of total probability. You could also just analyze, just like we analyzed last time, you could analyze the infinite tree of possible outcome sequences, but it's much cleaner to use the law of total probability. So here, the probability of heads is equal to, okay, now it turns out that unlike, the standard law of total probability with 2 cases, there are 4 cases. Okay, there are 3 cases. Either you get heads, you get tails after 2 tosses, or you restart. So it's the probability of, probability of heads is equal to the probability of heads given heads tails, okay, times the probability of heads tails, plus the probability of heads given tails heads, times the probability of tails heads, plus the probability of heads given restart, times the probability of restart. Okay, so now let's see if we can put probabilities to all of these. The probability of heads given heads tails, probability of heads given heads tails is 1, because you're outputting heads, so this is 1. And the probability of heads tails, this is p and 1 minus p. Okay. The probability of heads given tails heads is 0, because you're outputting tails and you're stopping. Okay, time whatever this is irrelevant. This is p 1 minus p. Okay, but now comes the interesting case. The probability of heads, given that you restart, times the probability of restarting. Well, the probability of restarting is p squared plus 1 p times p squared plus 1 minus p squared. So this is p squared plus 1 minus p squared. Okay. Now, what's the probability of heads given restart? Well, if you restart, the chances of heads are exactly the same as the chances of heads at the beginning of the experiment, because that's what it means to restart. So this is exactly the probability of heads. Okay, so what do we have? We have that the probability of heads is equal to p times 1 minus p, okay, times 1 plus 0 times something, which is 0, plus p squared plus 1 minus p squared times the probability of heads. Okay. So we actually didn't compute this. What we have done is we've gotten an equation for this guy in terms of itself. That's what the law of total probability allowed us to do. Okay, and we can solve this equation. If we take this term to the other side, we find, and I leave you to do the algebra, take this to the other term, and then you'll get 1 minus this coefficient, then divide both sides by that 1 minus this coefficient. You get that p of h is equal to p times 1 minus p divided by p squared plus 1 minus p squared. And you can do some algebra, okay, to show that this is exactly p 1 minus p divided by 2p 1 minus p, okay, which cancels. This is 1/2. As suspected. So this mechanism converts the biased coin. It may not be biased, but you don't need to now put your friend on the spot. It may or may not be biased. I don't care. This prescription, you do this experiment, and when it stops, it'll output heads and tails, and the probability of heads is exactly 1/2. We have converted a biased coin into a perfectly fair coin, provably fair. And so this is a mechanism you can use with any coin, because all coins are somewhat unbiased, and this guarantees that so all coins are somewhat unbiased because of physical imperfections, and this guarantees that you convert it to an unbiased coin, to a fair coin. Miracles of probability. Okay, checking out. See you next time.